Okay, let me see. Oh yeah, now I can share it. Okay, can you see it? Well, okay. Okay, is it fine?
Yes, yes.
Okay, good.
Yeah. Krishna, you want to do the honors?
Yes, yes. Hello, welcome all. So it's a great pleasure to introduce Nikita Kalinin of, sorry, the Guangdong Technion Israel Institute of Technology at Shantou, China. And he's going to give a talk on evaluation of lattice sums via telescoping over topographs. Over to you, Nikita.
Well, thank you very much for possibility to speak here. And I tried to present, let's say, a plan of my talk on the one slide. So the first slide here, and I will explain gradually all the terms which appear here. Well, by the way, can you see my cursor? No, or not? Can I? Well, maybe not. Okay, so on the right, you see the picture of a topograph.
We can see your cursor.
You can see. Okay, great. Okay, so here on the right, that's a picture of a topograph, and the topograph is just a three-valent tree, which is infinite, and which is suitable for studying quadratic forms. So it's quite recent. It was introduced by Conway, and despite its simplicity, it's like a very good tool to speak about many things. Okay, and the content is mostly the formula here on the top of it. So that we take a sum over all pairs of vectors in the first quadrant, such that determinant is 1, and then you take like 1 divided by the length of x, y, and x plus y squared, multiply by 4, and you have pi. So I enjoy this formula very much. And basically, all the content of this talk is grown from this formula. So some generalizations, explanations, and so on. And then on the second and third line, you will see nothing else, just another formulations of the same formula. So I will explain it. So the second formula appeared in the work of Adolf Hurwitz 100 years ago. And the third line appeared in the work of Don Zagier, well, like 20 years ago. And actually, these formulas, they're equivalent to the formula on the first line here. Okay, in a sense, it proves what is important, that this identities for arctan and hyperbolic arctan. So it's also, for me, it was a great pleasure to somehow relate it to classical stuff. Okay. Now, the next slide, that's about some corollary. So I will not return to that. But my work on topographs and this formula, it has a strange side effect that I discovered an identity for the gamma function and for a certain integral. So this integral WV1 appeared in the other work about topographs, like just some integral. And by studying topographs, I discovered identity which relates this integral with the gamma. And so since the seminar is called special functions, I could not resist to put here this slide. And actually the proof is very easy and short. You just expand all these functions in cosine Fourier expansion, and you see that the coefficients are the same. So you can compute the cosine expansion for the d gamma. So the sine terms disappear, and cosine terms, they are just cosine integrals. So I don't know, is it a classical fact or not, but at least I could not find it in sources, but it's easy to compute. You just check it. And the same expansion you have for this function W1. Okay, I will not return to that in the talk. Just a corollary of the results, which I think it's nice and maybe suitable for seminar about special functions. Okay, good. Now let's go to the plan of the talk. So first I give you an introduction about what I think about number theory, what I like in number theory. So that's supposed to be like easy for students, for grad students, for all students. Then I briefly present you class number for binary quadratic forms. Then I define the convey topographs, and then I explain how to get these identities from the first slide through some telescoping. So the idea of the talk is that I get this first identity via some telescoping over a picture like that. And it will be like quite apparent what's going on. So the proofs are easier than previous proofs. And then I talk about the gear identity, why it's equivalent to my identity. And finally, if I have time, I give you geometric interpretation of all these identities. Okay. Now, first, let me introduce number theory gently. I would say that for me, the number theory is about infinite sums. So you know the Basel problem. It's like almost 40 years ago, 400 years ago. And you just need to evaluate the sum of 1 plus 1 over 4, and so on, sum of the inverse squares. And then it's Leonhard Euler who found this sum and who proved that sum is equal to pi square over 6. And he defined zeta function of Riemann, and he proved a lot of statements about zeta function and Bernoulli numbers and so on. So for me, it's it's curious that it's called Riemann function, because it should be called maybe Euler function. Well, anyway, and still, even now, that's an area of research, because only recently it was proven that zeta of 3 is irrational. And I think it's not known about zeta of 5, whether it's rational or not. So it's okay. So still, this classical subject is very much alive. Okay, and then there are some recent methods to study this, and I find them very beautiful. I found that in the articles of Don Zagier, so 1993, but maybe it was known even before, so it's not something that kind of you attribute as a theorem. That's some computations. So let's define a function f, which is this rational function of m and n, and then one can check that such a difference sum is just 1 over m square n square. That's an explicit computation. I mean, you just compute it. And then you take a sum over this equality over all possible m and n. And so when you do it, you see that you have terms where m, for example, is bigger than n, then these terms will cancel by this term. There are terms where n is bigger than m, and then these terms will be canceled by these terms. And so finally, actually, so when you take a sum of all, this line over all mn, only terms with equal arguments survive. All the other terms cancel. And here you see that it will be just 5 over 2, right? Zeta of 4. So if you take a sum of f and n. And on the other side, here you will see just zeta of 2 square. So it means that just by summing this equality, you get a non-trivial relation between zeta of 2 and zeta of 4. Well, surely you need to show that here some convergence is correct, that you don't have some divergence and so on, but computationally just this. And I was fascinated by that, by this formula. So since I've seen this like method the first time, I was fascinated by this like telescopic things. So how can you telescope something to get new identities? Okay, and then what else? Besides summations over integers, you can consider summations over the lattice. Well, you can also think that the dedicating zeta function for Gaussian integers, or you may take a sum over just the lattice. So here you take integer points without zero, take here power s, and then you can see that this is just 4 times zeta of s times this L function, or you have this explicit presentation of it. Okay, and there are also similar lattice sums, but I mean, with also a sum over all pairs of integers, right? So this sum is the sum over pairs of integers. And there are other sums called Mordell-Tornheim series. So they were defined by Tornheim. So it's interesting how he defines that. First, he studied Fourier series and fourth circles. So, if you have a Fourier series, you can draw circles over the line, and these circles are tangent, like between themselves. And then you can evaluate certain sum of the areas of triangles, and then naturally you are led to define a function like this. And Mordell, he defined the same function a bit later from other perspective. Well, and it's called Mordell-Tornheim series. And there are a lot of relations between these values for different s. And so these relations, they produce here relations between multiple zeta values. So, for example, you consider T of 1, 2, 3, 2, 1, 3, 3, 1, 1, and then you find relations, and this, and then you can eliminate all these values T of like 1, 2, 3, and then the remaining will be the relations between zeta values. So, for example, also you can get this relation from this slide also in this way. So you can express z of 2 using this function t of something. You can express z of 4. Well, and then you find these relations. So it also became the area of active research. And then you can also ask questions about whether it's meromorphic. Yes, you can extend it analytically to the whole plane, no, to the whole space of parameters, except certain hyperplanes. And you can ask what are the values of these functions, let's say at negative s, and so on. So that's also a well, active area of research. And okay, and I tried to do something in the middle. So I wanted to have something about lattice sums, so summation over m and n, and also something about telescoping. And so I was looking for something of this form, but for inside the lattice. So I wanted to put here vectors like m and n, not integers, by lattice vectors. Well, and finally I found a formula. Now you see, so it will be maybe the heart of the talk and the heart of the paper. Okay, so let's prove this theorem. So we have the set of all vectors in the first quadrant such that the determinant is 1. So these pairs of vectors, they represent parallelograms of area 1. And then if you take a sum over all these like parallelograms, and you take the length of the sides and the length of diagonal square, then twice the sum will be pi over 2. And okay, so the proof will be telescopic. So how we do telescoping? We should define certain function f. So it will be f of 2 arguments, x and y. And we have the same telescopic identity. So we also have f of xy, x plus yy, and x plus y. The function f being this one. So just scalar product divide by the squares of the lengths of vectors. And then by explicit computation, you see that it will be -2 times determinant and divided by x plus y square. And since we restrict our formula for pairs of vectors with determinant 1, like immediately here you have just -2. Okay, and so then you just you telescope this like identity over all vectors, and this way you compute this sum. Okay, and 2 comes from 2 here. But here you need to do it a bit more accurate, because, well, how you do this kind of telescoping, you take a big square, right? For example, square with side n, and then you take a sum of this expression for all pairs of vectors of determinant 1, which are inside this square, and then you look at the terms at the boundary, right? Because you also have these terms, so all intermediate terms, they disappear, and these terms, they don't disappear. You need to estimate them. And actually, you can show that the sum of these boundary terms tends to minus pi over 2. And so this explains pi over 2 here. And okay, so brief explanation why we have that now. So let's go to the picture. So what happens with our parallelograms? So we start with a parallelogram spanned by 1, 0, and 0, 1. That's our vectors x and y. Then each time you just add vector x plus y, and thus you have 2 new parallelograms, right? So first you have one parallelogram, then you subdivide it by the vector 1, 1, and you have what is here like this parallelograms spanned by 1, 0, 0, 1, 1 and 1, 1, 0, 1. Then again, you subdivide each of them. So to this parallelogram, you add the vector 2, 1, just diagonal. And then you have these like black parallelograms. That's the step number 3. And step number 4, again, for each parallelogram, you just add the sum of well, the sides. So it will just diagonal. And then you have like parallelograms here. So each step you have twice more parallelograms. And you see, so if you look at the telescoping formula here, you will see that all intermediate terms cancel except the last generation of parallelograms, and except the first parallelogram corresponding to 1, 0, 0, 1. And so each generation of parallelograms, they just span the whole angle here. They tile, the angle. And now we just need to compute that actually the function f for such a thin parallelogram, it's equal to the angle of this parallelogram. So let's see how to do it. So here, all our parallelograms, they have area 1. So determinant here is 1. And then sine times x times y is 1. So it means that the sine of angle between x and y is like 1 divided by xy. Up to certain, well, so the angle is just 1 of xy plus certain error. And then if you look to the terms here, f of xy, that the scalar product divided by this, it will be just cosine divided by this. And then again, just 1 divided by the product of sides plus some error. So it means that f is actually the same as theta, up to the error. So it means that if you have a lot of parallelograms, then the sum over all of them, if they tile the angle, is just pi over 2. Plus some mistake which tends to 0, because this thinks the kind of cube of theta. So it means that the boundary terms, all these things, they converge to minus pi over 2. And for the first parallelogram, for the vectors 0, 1 and 1, 0, the scalar product is 0, so of f. So it means that the seed term, so the first one is just 0. So only boundary terms survive, and the boundary terms are minus pi over 2, and here you have minus 2 times this product. So that's how you get this formula. Okay, are there any questions here? Can you hear me? Or maybe I'm lost. Okay, so you're here. Thank you. Okay, good.
Yeah, we can hear you. Thank you. Sorry.
Okay, thank you. Because maybe I'm disconnected. Well, who knows? Okay, now let me relate this result to the classical stuff. Well, I was very proud when I discovered that, but then I start asking people, and I ask on Mataverflow, because maybe this result is not new. Maybe somebody else proven that. And it happened that yes, it was proven at least twice. So it was proven 100 years ago and 30 years ago. So now let me explain this thing. So how it's related to class number. So there is a theorem of Adolf Hurwitz of like 100 years ago. And if you have a fundamental discriminant less than 0, then all the terms in the following sum are positive, and this sum converges to h of d. To the class number, well, what you should know about h of d, that's an integer number, right? So here you have a constant omega d, which is usually 1, but for case of d minus 4 and minus 3, it's different. And what you have here you look all possible a, b, c, d such that b squared minus 4ac is equal to d. So that's our d is fixed. And a is bigger than 0, and you take a sum of such terms. Okay, and then multiply here by d power 3 over 2, and then you get the class number. Okay, so, and Hurwitz, he published this article, and basically nobody read it, so it had no citations, almost like 1 or 2. Now let me recall the notions about binary quadratic forms. So if you have a vector v, and let q denote the quadratic form, its q of v is given by am squared plus bmn plus cn squared. So these are the same a, b, c as you have here. So you will see it immediately. So then, as Gauss did, or even Euler, and before Euler, you want to define certain equivalents for quadratic forms. So you say that two quadratic forms are equivalent if you can find SL to Z matrix such that if you change the coordinates using this matrix, so M goes to AM plus BN, N goes to CM plus DN, so you change the coordinates, and then well, you say that the form with new coefficients is equivalent to the previous form. So it means that you are interested in the, for example, in the values of the form on the lattice. So you don't care what is the basis of this lattice, you just have a lattice. And then when you change the basis, your form is transformed in this way. And so explicitly you say that ABC is equivalent to this kind of triple for small ABCD from SL to Z matrix. So for example, you can see that if you put here a, b, c just 1, 0, 1, which corresponds to the form x squared plus y squared, well, m squared plus n squared, then here you have a squared plus c squared from here. It's 2ab plus 2cd. And here it's b squared plus d squared. And a plus b plus c will be equal to a plus b squared plus c plus d squared, right? So you see, so it means that when you look at the formula here you have a, c, and a plus b plus c. That's exactly, sum of squares of ab. Well, it's a plus b squared, c plus d squared, and the sum of their squares. So that's exactly the sum, well, the product of squares is here for two vectors. If x is AB and y is CD. Okay, so then we also have a number d, and d is a discriminant of a binary quadratic form. It's given by b squared minus 4ac, and it's invariant under the equivalence. So again, it's just a direct check. And then h of d is the number of equivalence classes of forms with the greatest common divisor of ABC1 and discriminant d. And it's clear that this number is, well, integer, positive integer. And formulas for h of d exist, but for example, if d is bigger than 0, it's still an open problem whether we have infinite number of d with class number 1 or not. I think it's believed that we have infinite number of them, but it's not known yet. Okay, so this formula above, that's a formula for negative d. But, well, I will tell you later that there are formulas also for positive d, but it doesn't help much, right? Because when you look at this formula, okay, here you have a series, but, well, it's a series of positive numbers, but maybe it's small, maybe it's big, so it's difficult to estimate such kind of series. Okay, so that was done by Hurwitz 100 years ago. So let's look for example. So if the quadratic form is just square of the length, so then the discriminant is -4, because it's like b squared minus 4ac, and b is 0, ac is 1. And then, well, you can also check just by hand, for example, that h of d is 1, so that all the forms with discriminant -4, they're actually equivalent. And then for the Hurwitz formula, we have, so let's say we know the formula that I just proved above. So that's a formula here about x and y, right? So this one. Because actually this set A, that's exactly the set of matrices A, B, C, D with AD minus BC is 1. And that's exactly the same set as here. Okay, so we know that this is just pi over 4. Then you look at the formula from the Hurwitz theorem. This formula, that's big A plus B plus C, and big C. And then you put all together, you have the following expression. So here that's the class number, which is 1. And here you have this, and this, and this. But then you also have some symmetries, because what you call A, B, or C, it's, well, you can make 3 cyclic orders. And then you put pi over 4 here, and 3. This is just d power minus 3, 4, this one, and w minus 4 is 2. Well, so you get correct inequality, correct equality, identity. So it means that the theorem I proved, it's actually the old Hurwitz theorem for the particular case of d equals -4. Okay, so now what is the story? So the Hurwitz result was forgotten. And for example, the paper was cited, I think, first time in the Dixon's book of History of Number Theory. So like 50 years ago, 50 years after the Hurwitz. And then the next citation comes in 1992 in Robert Čech's work on Eisenstein cocycles. And then next time it was revived in 2019, so not quite long time ago, in the Duke and Mamoglu Toth paper on the class number formula of Hurwitz. And so what they did, they said that, okay, so he has a formula for d less than 0, let's prove a formula for d bigger than 0. And yes, so they proved such a formula. So here on the left, you have, again, class number, but times the regulator, that's logarithm of epsilon d. And here epsilon d is a fundamental unit. So you take the Pell equation, You take the minimal solution in natural numbers, and then you take the logarithm of it. And then what you have, again, you have a sum over all AC, A plus B plus C bigger than 0. That's correspond to reduced forms. Again, you have here term like d power 3 over 2, and here the product of 3 like linear expressions. Also, you have some additional term here, that's ABC reduced, and here you have d power 1/2. Okay. So, oh yes, so this forms just all forms, but you need some normalization. So you say that AC are bigger than 0, right? Because here it's b squared minus 4AC, and right, yes. Okay, then the story develops, and like 30 years ago, in his book, The Sensual Quadratic Form, Conway introduced topographs, and topographs is a tool for visualizing binary forms, binary quadratic forms, if you are interested in the values over the integers. So you look for the values at the lattice. And topograph, it's just a way to represent a form, but somehow it becomes very powerful because, you know, it's easy to understand many things, like reduction algorithms for quadratic forms, other things. So it's much, it's pleasure to teach quadratic forms if you use topographs. So you draw pictures and then you explain everything on pictures instead of like computing formulas for reduction of forms. And then last year, Cormac Sullivan proposed unifying approach to the above formulas using topographs. Because you see, so here you have just sum over all quadratic forms which are equivalent to the given one. And so it's natural somehow to decompose all these things into equivalence classes and take a sum of this thing in one equivalence class. And then it should be equal to the logarithm of epsilon d. And one topograph represents exactly one equivalence class. Okay, now let me define topographs. So first in words, then I will draw pictures. And the topograph for a binary quadratic form, it's infinite planar tree with labels. So we label everything. So first we label regions, so in the complement, and each region corresponds to one primitive vector up to sign. Okay, so we don't distinguish v and minus v, and then we also label this region by the value of the quadratic form, because it's the same for v and minus v, so it's well defined. Then we impose condition that at every vertex, well, we have 3 adjacent regions because our tree is 3-valent. And then these 3 regions, they correspond to 3 primitive vectors such that like each 2 of them form a basis of Z2. And then the labels on 3 regions will be exactly Q of V, Q of W, Q of V plus W for a certain basis VW of V square. So this will also remind us the terms in this telescoping formulas. Okay, now let's look at the picture. So you have a vertex, and the regions, they correspond to vectors, well, plus minus v1, v2, v3. And then naturally every edge corresponds to a pair of vectors. Okay, so Conway has a term as superbase. So v1, v2, v3 is a superbase. And with a certain choice of sign, you have that v1 plus v2 plus v3 is 0. Okay, and then we label every region by the value of the quadratic form here on this region. And then you may recall the classical parallelogram law, because so if here we have v1, here v2, here we have the difference of them, here we have the sum of them. And then you have this parallelogram law, here that the sum of the label here and here is twice the sum of labels here and here. So that's true for parallelograms on the plane, but also it's true for any binary quadratic form. So that's true for any pair of vectors. Okay, so it means that since we have this identity near every edge of my topograph, it means that I can just define the values on the neighborhood of one vertex, and then I just can extend the labels on regions using this rule. So if I know these three, I know this one, then I know this one, and so on. So I just know everything. So that's what I say here. So once we know the values of quadratic form in a super base, it's three vectors with sum 0, and that's such that every pair of them give you a basis, then we know the quadratic form on all the regions. So that gives you a way to define topograph starting from this. So that's just another definition of a topograph. So a topograph, well, you can give this definition to high school students. So we have a planar connected 3-valent tree, and we have labels on vertices, edges, and regions. And then near every edge, labels must satisfy that R plus U is twice S plus T. And then, if you are given R as T near a vertex, you can propagate these values for all regions using this rule. And then also you can define values on edges. So here you say that on the value on the edge here will be S plus T minus R. So for the edge of this direction. So if you change the direction of the edge, you will have S plus T minus U. And actually it will be just minus the previous value. So if you choose the orientation of an edge, you have a number. If you reverse it, you change the sign of this number. And so you may start with R as a T, or instead you can say that you define just values on these three edges, and from this you can find also R as T and everything. And then you can check explicitly that if you define D discriminant of the topograph using this equality, then it will be the same for all vertices. This is just some local computation. So you look at two neighboring vertices, you denote the edges like that, and then you check that, well, using these definitions, you see that D for this vertex and D for this vertex, they are just the same. And so they are called the discriminant of the topograph, and they are naturally the discriminant of the corresponding quadratic form. Okay, then here I just propose you some identities on topograph. And again, you can just verify them explicitly. So here they're nothing except algebra and the relations which I gave you here. So we have a definition of D, we have relations between R, S, T, E, F, G. Well, and then, well, you have this. So for example, how you verify the first identity. So here G, S, T, F, R, S, E, R, T. You have a common denominator, and then you look here, and here it will be just minus D. Okay. So here you just say that R is F plus E by 2. Okay, now let's try to relate it to the formulas that we have before. So what is R, S, and T? R, S, and T, that are values on the regions. What are the values on the region? That's the values of quadratic form. So for example, that's the length of V1, V2, and the sum of them. So R, S, T, that's exactly what I have here in the denominator. Now, I claim that actually this topograph identity, that's exactly this identity. Okay, why? For the function f, I have the scalar product divided by the squares of the vectors. And here I have the same for x plus y and y, and x plus y. So this corresponds to the picture here. Right, so here I have like three vectors, and one of them is the sum of them. And now let's look at this identity. Here I have G divided by ST, or F or E. So what is E, F, and G? E, F, and G is what I have on edges. But what I have on edges? I have S plus T minus R. So for example, I have length of x square plus length of y square minus length of x plus y square. So that's exactly the scalar product. So, and actually you can just check that the values on the edges, that's exactly the values of the corresponding bilinear form on the pair of vector, right? So because every edge corresponds to a pair of vectors, and if I look at the associated bilinear form associated to Q, then the value, the label on the edge, that's exactly the value of this bilinear form. So it means that these terms here, that's exactly the scalar product divided by the length of vectors. So for the quadratic form, which is just the square of the length of a vector. But so this is true for any quadratic form. And I have other identities. So each time I have something on the left and something on the right. And the idea of the paper is that, well, we can telescope it. So if we telescope it, then just by the construction, we have some cancellation for terms inside, and we need to compute the boundary terms. And boundary terms, well, should be computed, well, also somehow, approximated by angles or sines or cosines and so on. Okay, and you have a lot of such identities, like for small denominators, for big denominators, like for cubes, like a lot of them. Now, what is interesting, these identities, they have a corresponding identities for arcsine, arctan, and also for their hyperbolic versions. So if you just have the same ERT, FRS, GST, so as you remember, it's just scalar product divided by the product of lengths of vectors squared. If you twist them by square root of minus d over 2, so d is a discriminant of the quadratic form, then you have such identity for arcsine or arctan, but for E, F, and G here. If d is bigger than 0, then you should put here big enough E, F, G, and then you have arcsine hyperbolic and arctan hyperbolic. And you also have such identity. Well, how you prove them? Well, you just say that this identity for arcsine is equivalent to that minus A is this one, because you just apply sign. You apply sign to the left part, to the right part, and then you know what is sign of arcsine and sign of the sum of two arcsine. You have this identity, and then you take square of it and cancel, then take square again, cancel. And well, you should say also that that's true for the corresponding branch, for the appropriate branch, because arcsine is multi-valued. So here sometimes you need to choose right branch. That's because on the first step you take a sign of well, this identity. Okay. Okay, good. Now, what was Sullivan's interpretation of these relations for quadratic forms? So he considered any topograph of discriminant less than 0, and then you take all the vertices of this topograph, and you take the product of labels, you take sum of them, and you have 4 pi. And so from here, the Hurwitz theorem follows, because this expression is just what happens for one topograph, then each equivalence class of forms corresponds to one topograph. So it means that if you take a sum of this thing over all possible values R, S, T, such that they represent a form of discriminant D, then on the right you will have constant times the class number. Okay, so that's here, right? So here you take again this A, C, and A plus B plus C, they represent the values of a quadratic form on a superbasis. For example, here on the base 1, 0, 0, 1, and 1, 1. And when you take a sum over all of them, on the left, you will have the class number. And you can do similarly for positive discriminant. Well, the proofs are, well, not that easy. So you need to compute some integrals over some paths on upper half plane and, do some computations which are not very transparent, at least for me. And my result is that I can do the same with topographs, like just via telescoping. So what we do, so here it's a part of a topograph. We will start with a root. So root corresponds to the basis 1001. Then here you have vector 1, 1, here vector 1, 2, 2, 1, and so on. So that just, this tree shows how to generate all the possible bases for Z2 in the first quadrant. And then I define a function. I take a sum of this function over the vertices here. Then I have some cancellation. So I have a term corresponding to the root and terms corresponding to the kind of crown of this tree. So the terms at the boundary. And it's possible to find the limit of terms at the boundary similarly in the simplest case. So that's the whole idea. So, and here that's a formulas. So you take a topograph of discriminant less than 0. You take half of it, right? So because I need to have a root seed. And let's say I have upper half of it with respect to a root E. Then I have some technical condition of admissibility, which is not important for now. And then for a suitable branch of arcsine, I have the following. So the sum of this RST over all vertices in this upper half tree is just 1 over d, then the value at the root, and minus 2 arcsine, the value at the root, discriminant, and so on. So it means that to compute such a sum, you just need to know the root, right? So because this value is E0, R, and T0, their values here. That's the values at the root. Well, and the same for sum of like this. So here also have arctan, and you need to know just the label on the root. You don't even need to know the labels on the regions. And from here you can deduce all the previous theorems, because now when you take sum over all topograph, you just consider 2 half tree, and you have such a formula for like 1 half, for second half, and well, that's it. So how you prove it? Again, you just need to telescope the function over the set of vertices. And then, for example, you telescope this function, like f of xy is e divided by rt. And so this will be just 1 of rst. And then you take a sum of it, and you have bounded at infinity. How to control the boundary at infinity? Okay, we need to understand what is E divided by RT when X and Y are very, very long vectors. Well, you just say that up to a constant, it's approximately arcsine of this expression. And then the sum of the things is just 0 at every vertex. It means that again, the sum at infinity, it can be put back to the root. That sum of signs does not change. And the mistake, the error that we have when we switch from ERT to arcsine, it comes to 0 by the same reason as here. So actually the proof is just just the same as here. So, but the notation is more general, but the idea is just the same. So we approximate this thing by sine or arcsine or octan or hyperbolic versions, and then we check that we have these things. So this equality actually is equivalent that when you subdivide an angle by 2, then the sum of two smaller angles is the initial angle. So that's nothing more than that. Okay, and also it's funny that this identity about arcsine is equivalent to also the famous identity about cotangents. So also I like it a lot. So these products of two cotangents, they correspond to terms here. And this one corresponds to this term. So you just need to multiply. And well, so, and we inside we need these identities for arctan. Also, they are just equivalent to, things here. So that this sum is 0, because you know when the sum of 3 arctan is 0, so you just need to check that here you have 0, and that just comes from these telescopic identities. Okay, now let me briefly tell you about how to get Zagian identity out of it. So what is Zagian identity? Is this one. So consider the fixed z. It's a complex number. And then consider the lattice generated by z and all triples of vectors with some 0. And prime means that I don't allow a vector to be 0. Then I can take the product of them, take the modulus, and then take a sum of all such triples. And you also put here imaginary part of z. And then that's equal to this Eisenstein series plus p cube z of 3. So that's Zagian identity. And actually it's equivalent, right? Because here you have 3 complex numbers, and here you have product of 3 squares of lengths of vectors. So here you have the determinant 1, and here you don't have this condition, but you have something like more complicated on the right. So it can be actually proven that it's equivalent. So how you do it? So let's see. So again, you just show that what happens if, again, you consider the pair of vectors in the upper half plane such that the determinant of xy is n. You can just classify all the lattices with determinant n, and there are exactly sigma 1 of n such lattices, right? So you choose the vector 0d, and then you have n divided by d such lattices. So the second vector has like choice n divided by d. And then for each such lattice, again, you have the same consideration of parallelograms and the same telescoping, but the constant will be different. So here you have n squared, and here you have pi by 2n. But at the end, it's just the same computation. And then you say that when you put in Zagian identity I, it means that you consider just standard lattice, z squared, like z plus zi. And then, so that this Eisenstein series corresponds to the vectors when they are collinear. And so if you subtract it, you have exactly this constant times sum over all n of such a sum over lattice of area n. Right, and then we already know this formula, so we just need to substitute it here. You substitute it here, and you have, this sigma 1 of n divided by n cube. So you know that z of 3, z of 2. And, because you know the sum of this Dirichlet series for the divisor function, and, you have the same constant as in Zagier paper. And we can do also it for the not necessarily lattice of determinant of area 1, but for any. So, and actually you can just put here any vector z, any s bigger than -1, and then you have such a formula. And then if you put here s equals 0, for example, then you have the identity of Zagier, and y cube goes here. That's exactly the imaginary part of z. Okay, and finally the last slide here, that actually there is a simple geometric interpretation of all this, which is contained in the paper of Hurwitz. Maybe a bit obscured, but it's actually this one. So let's prove this theorem of Hurwitz. So we have here A, B, C, D. And so they represent the rational points, right? So if you have a rational point A, B, there is a point on the unit circle corresponding to it using the standard rational parameterization of the circle. So this one. And then, 0, 1 goes to 0, -1, 1, 0 goes to 0, 1. So actually just a half circle. So right half of circle. But then you can check that if you have points A, B, C, D, and A plus C, B plus D, well, that's the median between these two rational points, then the area of the triangle with such vertices on this circle is given by this. So that's exactly the AD minus BC is 1, because we consider only such pairs of vectors. And well, so here we have exactly this RST. So this formula boils down just to the following. So I cut half a disk into triangles. So using this parameterization and, well, this Fourier subdivision of interval 0, 1. And then I just compute the areas of these circles, and the areas of this circle is pi over 2. But also I have 2 here. So that's finally it's pi over 4. So, and that's the geometric meaning of these things. And, well, so thank you very much.
Thank you, Nikita. It's a lovely talk. Any questions from the audience or comments?
I just want to make one comment to Nikita that there's a paper that I have on. It's called on an elementary identity of Euler, which is on telescoping. And also, Krishnan and I have a paper on telescoping continued fractions. So, but in neither of them we telescoped on the plane. So this is very interesting. And
yeah, so please send it me because I want to, to run it.
Yeah, definitely. Yeah.
And would there be any, higher zeta values? Of course, you had one for zeta s plus 3 into s plus 2. Does that give any interesting identities for higher zeta values? Interesting as in new identities, sorry. Very interesting, sorry. New ones.
Well, so you see, so in a sense, I defined a new function. So this new function can be expressed in old values, but no relations.
No relations. Okay. I see.
Okay, let me also tell you another part of the story. So starting from this identity of Zagier, there is the whole topic of modular graph functions. So this is a modular graph function corresponding to the graph with 2 vertices and 3 edges between them. But you can consider other graphs, and you have such a function for any graph. And you also take a sum, you have conditions for vectors, and then you take something with denominators of the modulus of these vectors. But the conditions are more complicated. And there are hundreds of articles about that, and there are a lot of relations of zeta values and Eisenstein series and many other things. It's a vast literature, and I hope that these telescoping functions can be used there. Because usually what they do, they have just telescoping over all possible things. And I can do it just for half of the graph. And so maybe this way, if I could employ this technique for the modular graph functions, then I will have also at least finer relations, because they have a lot of relations for zeta values, but so far I could not, improve something or get something new. But it's very interesting. So kind of in this direction.
Very interesting. Yeah, thanks. Anyone else? If not, we thank the